Hi guys, so the first thing that I'm going to talk about in today's PowerPoint is polyprotic acids. This is going to consider polyprotic acids, we're going to look at diprotic acids, and we are also going to look at triprotic acids. So they mean what their name entails. So polyprotic acids are really just any acids that are going to have more than one ionizable hydrogen atom or molecule. So basically we're able to pop off more than one hydrogen. So in our first example here, this is how we make um, sulfuric acid, but we're actually going to look at its sequential ionization. So in this first equation here, we have sulfuric acid, and it is going to lose a hydrogen ion, and then we have our conjugate base of hydrogen sulfate. So we know that hydrogen sulfate is the conjugate base, but in our second ionization equation, that hydrogen sulfate is going to act as an acid in that scenario, and it will also lose a hydrogen ion. And then we just have our other conjugate base of sulfate. So one thing that I want to emphasize on is the first Ka is very large, and the second one is smaller. So we know that the first Ka, we know that sulfuric acid is a strong acid, so it's really likely to lose that first hydrogen ion. But upon losing it, then when we have hydrogen sulfate, that is going to be less likely to lose its hydrogen ion because of that negative charge. So think about the larger our negative charge is becoming, the more unlikely it is to occur. Just because in solution, that large of a negative charge is not preferred. So these are a couple examples of our diprotic acids. You have their different Ka constants. Always notice that Ka1 is larger than Ka2. Okay, so for example, some of our diprotic acids, we have carbonic acid, we have sulfurous acid, and as we saw in the last slide, we had sulfuric acid as well. And we've already talked about Ka1 being larger than Ka2. It's more difficult to remove an H plus ion from a negatively charged anion. It wants to hold on to it a little bit tighter. So typically only the first H plus affects pH. So we can kind of think about that as Ka2 being so small that we are going to have a negligible change. So here's an example of a triprotic acid. This is citric acid, and citric acid has the capability of losing 3 hydrogen ions. So it is what we would call a triprotic acid. Typically, we will just refer to these as polyprotic acids, but if you really want to get specific, we can refer to them using di or tri or however many hydrogens it is that we are losing. So we are going to do this practice problem. This would be a good point in the video to pause and kind of see, do you know how to get started? What information are we trying to solve for? Stuff like that. So give it a pause before I show you kind of how to work through it. All right, so we're going to calculate the pH of a 0.1 molar carbonic acid solution. So if we didn't know already, the question really tells us that carbonic acid is going to have 2 ionizable hydrogens. So 2 hydrogens that we're able to break off. So the first thing that we would want to do is we would want to write both equations and assign Ka's to our appropriate equations. So as indicated here, they have a little bit of an overlap. You don't necessarily need to do that. You could set it up as 2 separate equations, or you can indicate via this kind of one long equation. But first set up your 2 equations and set up our equilibrium expressions for our Ka's. So we know from the first one, we're starting with 0.1 molar of carbonic acid, so we can really use that as our starting point, right? That is what we're starting with. That is how much carbonic acid we have being put in. We can tell from the Ka and also from our knowledge that carbonic acid is not a strong acid. So it's important for us to set up our ice table, not shown here, but that's how you get all those variables and those x's. It's important for us to set it up in that manner because we already know that we are going to have a small change in terms of our hydrogen carbonate that is produced. So because our Ka is small and we know that we're dealing with a weak acid, we can just kind of drop that bottom x to make our math a little bit easier. And upon solving for our hydrogen ion concentration, which we know has to be equal to our conjugate base, right? As we lose hydrogen ions from that acid, we're producing conjugate base. So those two are directly related. We get that to be equal to 2.07 times 10 to the negative fourth molar. So in our second expression, our second Ka expression, we can see right where we're going to plug that in. They are using y's here just to keep it separate from the x that we solved for previously. If you wanted, you could set this up. We're going to solve for it the same way. So you could use x again. They're just using y to make sure that we know that it's not going to be equal to the x that we already solved for. So this one, again, same thing. You can drop the y on bottom because we are assuming it to be extremely negligible. And this, we get our y to be equal to 9.86 times 10 to the negative eighth. So from both of these, then we know our hydrogen ion concentration, and we can add it together to get our total. And from our total, we can solve for the pH of our solution. So the pH of our solution, using that total solved for hydrogen ion concentration, is 3.68.